In the last video, we proved this theorem. We proved that lambda was an eigenvalue for A if this determinant was 0. This is a polynomial lambda. Let's give it a name. So again, we'll call this polynomial the characteristic polynomial. Let me use an x just because we're used to having x inside a polynomial. Alright, so the determinant of A minus xin, that's going to be called the characteristic polynomial. So characteristic polynomial of A. The important fact about this polynomial is its roots are the eigenvalues. So let's write it just to make sure we remember. The zeros of PAX are the eigenvalues of A. Alright, let's try an example. We'll find the eigenvalues and eigenvectors of one matrix. If you want to try it yourself first, just pause the video, try it, and then you can run the solutions afterwards as you wish. Alright, so where's my matrix? One, 4, 2, 3. I'm going to start by finding the eigenvalues. I need the characteristic polynomial, so PA of x is the determinant of A minus x I. We have a 2 by 2, so I2. So that's going to be the determinant of 1, 4, 2, 3 minus x, 0, 0, x. Let me use the straight lines to determine, to indicate determinant. So I'm looking for the determinant of 1 minus x, 4, 2, 3 minus x. Alright, so let's expand. We get 1 minus x, 3 minus x. That's the downward diagonal. Minus 2 times 4, that's 8. So I get x squared minus 4x plus 3 minus 8. So I get x squared minus 4x minus 5, which is x minus 1, x minus 5. One of them has to be plus. To get the minus, I'll get this. Alright, so that's our characteristic polynomial. we want the eigenvalues. Those are going to be the zeros of the characteristic polynomial. So I have two eigenvalues. I have lambda could be -1, or lambda could be 5. We have two eigenvalues. They both have eigenvectors, so let's find one eigenvector for each. All right. So from lambda equals -1, remember in the theorem, we got a bit more than just a way of finding the eigenvalues. We got that the eigenvectors were part of the null space for a minus xi. So here, if I look at a minus lambda I2, that would be 1, 4, 2, 3 plus 1, 0, 0, 1. So that would be 2, 4, 2, 4. Now, each time you do this, you should be getting a matrix which doesn't have an inverse. 2, 4, 2, 4, the rows are parallel, no inverse. Perfect. Now, I want to find a vector in the null space of this. I'm going to reduce it. I have a free variable, so I'm going to use S for that. So my matrix, my vector xy needs to be -2, 1 times that S. So for any choice of S, except 0, you would get an eigenvector. Let's pick S equals 1, the easiest. And we found our first eigenvector by ourselves, so we found -2, 1. That's an eigenvector for A corresponding to the eigenvalue -1. We still have lambda equals 5 to do, so let's try that one. That was so for lambda equals 5, I'm going to look at a minus lambda I2. Always the same thing, your lambda changes. So in that case, I would get 1, 4, 2, 3 minus 5, 0, 0, 5. I'll get -4, 4, 2, -2. Again, the rows are parallel. Perfect. So I'm going to reduce it. I need to find a vector in the null space. Again, I have a free variable, so xy will be -1, 1, s. So it doesn't matter what value of s you pick as long as you don't pick 0. An eigenvector is not allowed to be the 0 vector. So for s equals, you could take 1. Let me take minus 3. It doesn't matter. You could take pi, you could take e, anything you want except 0. We would get that 3 minus 3 is an eigenvector. For A. Alright, so we have 2 eigenvalues. We found 1 eigenvector for each. Now just to make sure we realize what this means about the matrix, let's graph the action of that matrix on our 2 eigenvectors. I had minus 2, 1, and 3 minus 3. Alright, I have my special colors. Minus 2, 1, let me draw it in red. Minus 2, 1 is over here, minus 2, 1. On minus 2, 1, the lambda was equal to minus 1. Let me double check. Yeah, the lambda was equal to minus 1, so that means this one's flipped and is now 2 minus 1. On 3 minus 3, the lambda's 5, so that means that 3, 1, 2, 3, minus 3 will get 15 minus 15. And this one was minus 2, 1, and it's sent to 2 minus 1. Alright, so that tells you what the entire plane does. The line in the direction of minus 3, 3 is stretched. The line in the direction of minus 2, 1 is flipped. And everything else is a combination of a flip and a stretching.